My name is Emmanuel and I'm presenting our upcoming SIGMOD 25 paper about SpareLLM. This is a work by my recently graduated student Saihan Yo and by myself. And when it comes to large language models, you definitely want to make sure that you are not using a model that is larger than you need, because the difference in pricing per token between different models is quite significant. For instance, when taking even the models from a single provider like OpenAI, you already see a price difference of several orders of magnitude. That's why we are proposing SpareLLM, which is an architecture that helps users to select the cheapest model that does what they need to for a certain task. So we assume that we have a task that is accomplished by a language model on a large collection of data items, and we have a couple of alternative models that we can choose between. So the input to SpareLLM is data together with a reference model, which is the model that you believe would do best for the task we have in mind. Could be a large model like GPT 4.1, for instance. But using this model typically is quite expensive, so ideally we want to use one of the smaller models. So we assume that users provide us inputted data with a task description together with an equivalence constraint, and the goal is to select the cheapest model among all alternatives that produces the same output as the reference model in a certain ratio of cases with a certain confidence. So that is the equivalence constraint. Now I'm gonna present multiple versions of the SpareLLM architecture, starting with something simple, and then we're gonna extend this in multiple steps. Now in the simplest version, we can use profiling in order to assess the ratio of cases in which different language models produce the same output as the reference model for the given task. So we can do a little bit of profiling, and then we can select the cheapest language model for which we are sure that it satisfies the user-specified equivalence constraint with the reference model, and we apply that to the remaining data items. Now, when I say profiling, I mean that we are essentially, first of all, applying the reference model to a certain data item, and then we are applying a subset of the smaller models to the same data item. And then we are comparing whether the output of those smaller models is consistent with the reference model. So here I have an example scenario after we did a little bit of profiling. So profiling generally gives us a confidence bound on the average ratio at which one of those cheaper models produces the same output as the reference model. And in this plot, I have ordered my models from cheapest on the left to most expensive on the right, and you always see my confidence bounds on the equivalence ratio for each of those models and the user-defined equivalence threshold. And you see that for some of those models, those confidence bounds are below the equivalence threshold, so those models are not equivalent enough to be used. For other models, I have a confidence bound that overlaps with the equivalence threshold. So for those models, we might want to do a little bit more profiling to decide whether or not they can satisfy the equivalence threshold in average. And then we have some models, one particular, which is clearly above the equivalence threshold. And if profiling stops now, then I would essentially select the cheapest model for which I'm sure that it satisfies the equivalence constraint, and that would be the model over here in this case. Now, this is the simplest version of the architecture. It assumes that we are profiling all of those models, but in some cases I can already say after doing a little bit of profiling that I don't need to do any more profiling for some of those models because they are not interesting anymore. And that can happen for several reasons. So here we have again an example where we have confidence bounds on the equivalence of different models, ordering models from the cheapest on the left to the most expensive on the right again. And here clearly we have one model that is not interesting because it doesn't produce output that is sufficiently often equivalent to the reference output. On the other side, there is a model where we already know that it produces output that is quite consistent with the output of the reference model. And because of that, we know that we don't need to do any more profiling for those more expensive models where we are not currently sure whether they produce sufficiently high quality output for the specific task that we are looking at. So in that case, I wouldn't have to include them in any further profiling. So in this extended version of the SpareLLM architecture, we are regularly pruning some of the candidate models from further profiling because they are not interesting anymore. Now, another thing about profiling is that doing it is quite expensive, because in order to assess whether the output of those smaller models is equivalent to the reference model, we first have to apply the reference model, which tends to be quite expensive. So because of that, we're introducing a check that regularly tests whether further profiling is even beneficial or whether it's not beneficial, and we should immediately use what we know so far in order to determine the best model to apply for the remaining data items. Because when using profiling, then it means that the more you profile, clearly the more money and time you spend in profiling. On the other side, the information you gain via profiling, it is beneficial in the application phase, which starts after profiling, but there are probably some diminishing returns. At some point, I will know for most models that whether or not they are eligible given the user-defined equivalence constraint, and then further profiling, it gives me less and less valuable information. So the amount of money that I can save in the application phase via further profiling, it tends to diminish over time, as it is illustrated in this plot. And there's probably an optimal point in time at which I want to switch from profiling to the application phase. And SpareLLM uses cost-based optimization in order to try to optimize the point at which I want to switch from profiling to the application phase. Now, so far I have assumed that I will select one single model that I apply to the remaining data items that haven't been used in profiling, but that is maybe more restrictive than necessary. So the final version of SpareLLM doesn't actually select one single model, but it selects a mix of different models in order to process different ratios of the remaining data items, because even if one specific model may not be able to satisfy the equivalence constraints, maybe in combination with some other models it can satisfy the equivalence constraint and become cheaper than any single model. Now here's a little example to illustrate this point. Now let's assume that users have specified an equivalence constraint of 91%. So with a certain confidence, we want to produce equivalent output to the reference model in 91% of cases. And after profiling, we know that GPT-4, which is the reference model, we know from the start that it will produce the reference output in 100% of cases, of course. And another model, the GPT 3.5 Turbo model, it produces equivalent output to the reference in 90% of cases. On the other side, the GPT-4 model is 30 times more expensive per token compared to the cheaper model. So ideally we would like to use the GPT 3.5 Turbo model, but the number of cases in which it produces the reference output is slightly below the equivalence constraint. So if we had to select one single model, that would have to be the GPT-4 model, which produces the reference output in all cases. But if we can select a mix of different models, then we can process about 10% of the remaining data items with GPT-4 and 90% of the remaining data items with GPT 3.5 Turbo. And doing that results in significantly lower costs overall compared to having to use the reference model in all cases, and that shows that using a combination of different models can be beneficial compared to using only a single model. Now, in the experiments, we first of all compare different versions of the SpareLLM architecture. Those are the different variants that I explained on the previous slides. And here we have only one experiment where the goal is to classify movie reviews into positive and negative reviews using language models. Here using different models from OpenAI, from Babbage, the cheapest one, to GPT-4, the most expensive one. On the x-axis of the plot you have equivalence constraints, starting from fairly restrictive on the left-hand side and then becoming more relaxed on the right-hand side. And on the y-axis you have the costs that we get with different variants of the SpareLLM architecture, and using GPT-4 everywhere, which is of course the most expensive version. On the other side, as you use the different variants of SpareLLM, if you use those different techniques that I have described on the previous slides, then using more of them makes things cheaper. And for each of those extensions that I discussed, there's at least one scenario where making that extension leads to significant cost savings. And this is just a small extract from our experiments. In the paper, we present many more experiments that show the same tendencies. Now, beyond comparing different variants of SpareLLM, of course, we can also compare the different baselines. And here we use two recent baselines, Frugal GPT and Cascade-based baseline, which essentially uses a sequence of different model invocations in order to get a better cost-quality trade-off compared to using just one of the more expensive models. And here we have cost on the x-axis and the accuracy when treating the benchmark on the y-axis, again for classifying movie reviews. And here again you see that SpareLLM performs very well. It makes up most of the Pareto frontier in terms of cost quality trade-offs compared to those recent baselines. And in the paper we have many more experiments with different scenarios that corroborate those tendencies. So, in summary, don't overpay when using large language models. It doesn't always have to be the largest model for each task. You can often get almost the same output with some of the much cheaper models. And SpareLLM helps users to do that. It saves costs with equivalence guarantees. So you specify a ratio of cases in which your model should produce the same output as the reference model, and then SpareLLM finds the cheapest model that can achieve that for you under those equivalence constraints. And it uses a couple of different ideas to do that in scenarios where we have to process the same task on a large collection of data items using large language models. It assesses the quality of different candidate models via profiling. It tries to be smart about how much profiling it does in order to avoid overpaying on profiling, and it considers ways to combine multiple models together in order to get optimal cost quality trade-offs. That is the SpareLLM paper. We will be at SIGMOD. Please talk to us in order to get more information.